Okay, in this section, we're going to talk about sliding window attention, rolling buffer, and KV cache, which we all use all of them in more modern LLMs like Mistral, Llama, and even DeepSeek, and so on and so forth. But yeah, let's jump into it and see what are they and how they perform. So about the sliding window attention, it's just a kind of attention that allows you to do the attention but with less computation. So imagine, I don't know, we have the just about these diagrams. Imagine that we have keys and queries, and also imagine, for example, I don't know, imagine that we have different tokens and they attend each other. So one way of doing that, the attention, is each of the tokens or keys can attend each of the queries, which we call it full attention, which technically is a little bit, I can say, nonsense, because we don't usually use such a thing. We mainly use causal attention and a sliding window attention, and the reason that we have causal attention, as you can see, the tokens they attend anything that is before the current token. So we don't go further because there is no point of going further, because, for example, in many of the transformers or LLMs, they are generators, so they generate something, so there is no point of looking forward, so there is no reason to look forward in the attention. That's why we put a causal mask and we literally turn all the future, let's say, tokens into 0, so we can predict what are the next tokens. And there is another version, but as you can see here, as we go forward through the, let's say, sequence, we have more tokens to look at, which can cause, I can say, too many operations, or it's not very efficient. But about the sliding window attention, imagine that we have a window size of 4, and as you can see, each token just only attends the previous 4 tokens, and that's why we call it sliding window. The window size is 4, but so it's very efficient and optimized. But you might say that, okay, if we only look at the previous 4, for example, let's say here in the last one, if we just look at the previous 4, how the hell we can have the full context of the previous tokens, which I will explain in a minute. The other version of the attention is dilated attention. As you can see, it is just simply putting holes into the attention, for example, attending them one by one. We attend the next 2, next 4, but not anything in the middle. It's again a kind of a strategy. It depends what you want and what you want to do and how optimized you want to make it. But yeah, you can technically do whatever you want in whichever you want. You can do a dilation on the sliding window as well. So it's up to you which one you're going to choose. But yeah, but the main one which we're going to talk about, it's the sliding window attention, and we want to see that, okay, how tokens can attend, can have the full conversation or the full context. And the key to that is just the layers. So imagine that, okay, so we have 4 layers here, and imagine we are in this very last token here, which technically attends, as we said, and by the way, imagine that the window size is 4. So technically, this token attends the previous 4 tokens, these 4, okay? And we want to see that, okay, is there any way that we can have the full context and have the full memory of what's going on in this sequence or not? So if we are in the 4th layer, we have information of these 4 in the previous layer. We get the information from all those. But the thing is, these 4, they literally have much more information from the previous layer, so the layer 2. So for example, this one, again, the last token in the third layer, it has information about these 4. And the very first one here, this one, it has information about these 4. So technically we can say the last token in the 4th layer has information of all these tokens. And by the way, it is just the layers and we just repeat it. So it literally has all information of all these tokens. And if we go just further one more layer down, so again with the same reasoning, we can say that okay, that last token in the 4th layer has information of all tokens because of the propagation of the information in fact layers, because of the data flow. And that's technically how we can make sure that okay, we have the full context and the full information of, let's say, whatever the sequence size is, or in fact, yeah, it's a kind of trade-off, the sliding window and the number of layers. It depends on how much memory you want to have, and I don't know how much computation and optimized you want it to be, so on and so forth. But let's go a little bit deeper to even better understand it. So imagine that for that sliding window attention, and let's say the window size is 3. Let's say window size is 3 here. And imagine the sentence is I love tennis and golf, which I do. And so, okay, the window size is 3. So this is our first layer. Then the second layer. So let's say for the first one, in the second layer, because the window size is 3, so this one would be technically what we have. This one would be the information from the previous layer. So it is I and love both of them. So it has information of both of those, in fact, what's that, positions in the previous layer. But this one, here, by a sliding window, I could simply say anything before the current token. But what I'm doing here is a little bit slightly different, and it is just for, what's that, demonstration. So the current token, when I'm saying a sliding window in the current token, what I do is I look one before and one after the token. So you can easily do 2 before or 3 before or previous token. So there is no, in fact, not much difference. So what I'm here doing by window is, if I say 3, window size of 3, I do, if I'm in the current position, let's say here, I look one forward and one backward. So here, the information that I would have is I love tennis. And here in this one, so that would be technically these 3 right here, which are love, tennis, and ant. But if we go further one next layer, so the first one again have information about these 2, so which is I love, which are again here, and tennis. So it has 3 I can say tokens or words or whatever that it is. And the second one and the third one, let's talk about the third one. As you can see, the third one, if we go one back layer, it has information about the one token, in fact one position before and after, which if we look is technically the full sentence. So this one has the full information about the full sentence. So yeah, even if we go one further layer above, so we can have even each of these in fact positions, they would have even more information and the full context of the full sentence. So that's how technically it happens. So there's no worries about if we have a small sliding window, would that affect the context or memory of my model? No, that's fine. It depends how many layers you have, so you can fix it, and there is no worries about it. And yeah, it is here we have all different types of attention mechanisms and attention types with, I don't know, the patterns and the cost of them. So for example, full attention, it's O of n squared. The causal is again the same, but the sliding window is n times w, and w is the window size. So as you can see, it is much better low memory kind of attention, and that's why we see those improvements in Mistral or Llama, which are faster and more efficient. This is one of the reasons technically. And by the way, we will go further deep with some more visualizations, so bear with me. We will get to that after this introduction for all of them. So the rolling buffer. So imagine just the rolling buffer is a kind of mechanism which is a fixed size data structure which overrides the old data with new data in a, as you can see, cyclic manner. So what happens if we have a long sequence? What we can do, because of the limited memory, we can put it into a kind of circular buffer, and this would allow us to be more efficient technically. That's technically what will happen. And as you can see, it's useful in streaming data, which we have in technically all LLMs, real-time systems, and so on and so forth. Again, bear with me. I will show some visualizations which will in fact give much better understanding of how this rolling buffer would work. And also the KV cache. So what KV cache technically means is that when we want to calculate the attention and those key and value in fact multiplications, we have lots of repetitive calculation. So what we can do is we can save and cache lots of those steps and repetitive steps and avoid recalculating them. So this is technically the mathematical formulation of it, but more visually, if I want to tell you, I can just quickly go down here. Just imagine that, okay, this is the query and key of mine, and let's say okay, for example, if so these are technically the new tokens which are joining, but let's say if I can just okay, let's say if I want to calculate this position right up here, so what I need to do is technically it's just the first row, the first query times the first column or the key. Then I will get this position, and imagine that all I have is the first let's say token. So when I have the first token, it is literally this part and this part. When I generate the next token, let's say I did all the calculation and I times it to V and I get the output. So what I do is I append this back into right here and also right here. Now I need to do the next step to calculate the next step. So how that one would look like is, so now I have the second one, and if I want to get these two positions, so what I need to do is again doing a multiplication of the first row, first column here, and then what I can do is technically first row, second column, I get this result, second row and second column, which would give this result to me. But as you saw, I recalculated this part. But what I could easily do was I could simply cache that value, and that one was from the first row and the first column. And that's how KV cache happens. I don't need to recalculate this part. Or for example, if I want to imagine that I went the second flow, second pass, and now I have to, let's say, second value and second output, And then again, I append it, and remember this is a generation, we just append it again and again and again, and now, and also at the same time here. So for the next one, we have 3 by 3. Imagine we don't have these, technically the rest of these matrices, we only have 3 of them on that side. So now, because it is 3 by 3, what I can calculate is I can calculate these positions as well. So I have total of 6 positions right here to calculate, which 3 of them, which are these 3, are just repetitive. So I don't need to calculate them. So all I need is just simply calculate these 3, and those 3 on top, I can simply add them from the cache. So this is called KV cache, and we can simply just cache all those results, and it will make the whole calculation much more optimized, and it is very beneficial. And again, as I said, there are some visualizations which I will show you in a minute, and you don't need to, in fact, I know it's hard, so bear with me, and we will go through the code and visualizations to understand it better and better. So yeah, about the visualizations, let's just quickly go here. So about the sliding window attention, so this is the code, you can have a look at it. I will put all these documents, I don't know, HTML file, PDF, so on and so forth, in the technically, what's that, my GitHub repo, so you can, and I put the link in the descriptions, so you can go there and have a look. But yeah, let's see how this technically a sliding window attention looks like. So this is technically sliding window attention together with the circular buffer for KV cache. So as you can see, let's say the sliding window, let's say it is equal to, let's say 5, and we are in the very first token. So this is the first token, and this is technically our circular buffer. And imagine, because we have the limited memory, we cannot have the whole sequence, so we have them in a circular manner. We add the next token goes to the next position. And by the way, because it is on a list, it's in a list, I can say, structure, so technically, in reality, it will be appended to the first, I can say, cell of the list. But here, because it's a circular, it is more near to reality and what will happen. Later on the code, we will see that how this happens. So the next token goes to the next, in fact, cell, and we calculate the next token. It is on the index 2, index 3, index 4, index 5, which is, again, because we have limited memory, it goes to, and it is a circular buffer, it goes to the first effect position. And again, as you can see, because we have a sliding window attention, so this is technically how it works. And by the way, we have all these in the cache, so we have all these sequences in the cache in all these positions. And as we just go forward, this is technically how it happens and how it works. So it makes sure that the calculation of the window allows us to make it more optimized with less computation, and the circular buffer helps us to deal with, in fact, limited memory, but at the same time being able to attend long sequences. About the, in fact, the attention, so which I showed you in a minute. So as you can see, this is the first, this is the full attention. So imagine we are in the second token. Let's say this is the second token, and as you can see, we have all these cells calculated. So technically, for the next step, imagine if we are in the KV cache, for the next step, we only need to add that last, see, these 3 cells. Everything else is just repetitive. which we can gain it from the previous step. So we don't need, so we can cache all these values and we can just compute these last 3. For the next step, we can cache all these 6 values, or technically Q and K's. And the only thing that we need to calculate is further 4. And that's all. So this is technically the concept of the KV cache and how much more optimized it can make the whole process. And yeah, so this is technically how it happens. We just give one Q, which is the output of the previous step, and just do the calculation with the cached version of the keys. We get the scores. We have the cached V's. We generate the output. We append it back, and just this whole loop goes on and on and on. And also the sliding window, it is just again kind of representation. Again, imagine that we have the window size of 4. This is technically how the whole sliding window attention would look like. As you can see, once we're done with the 4 tokens, it will stay the same. So it is much more optimized in terms of calculations. And just one furthermore, again, if you want to have this full document, you can find it on the link to go through all the steps and how much, for example, memory it saves and so on and so forth. And this one again is just simply, again, imagine that window size is, let's say 5, the current query tokens in the window, and cached slots. So we have just only one cache slot, and this is the current one. So we go forward, and as you can see, so this is technically the step that we filled the cache, we filled the cache. The next step will override it from the first place. But again, do not forget, when we override the first index, the logical sequence and occurrence of the sequence will break. So what we need to do, we need to rotate it to make sure that, for example, here it is technically 1, 2, 3, 4 and then 5, but 5 comes first. So technically we need to rotate it to make sure that the occurrence of the sequence is valid, and that's what we call it on rotate, and we will see it in the code. Just remember what it does and why we need that, because it will be appended to the first index. So the occurrence and the logical sequence of the sequence will be somehow broke. So we need to fix it. We need to unrotate it. And this just tokens, we can generate them, and this just happens on. This goes on and on and on. So yeah, let's just quickly go to the code. So what we covered was a sliding window attention, the KV cache, and also the rolling buffer. So again, I put the code. What I did is, this code technically is from Mistral itself. What I did, I add some more comments and explanations, so it's easier to understand. So feel free again to get it from my GitHub. So technically what we do here, so the cache file, cache.py, explains how the cache, what is the logic behind the cache. Again, this code is a little bit, I can say, it's not that easy to understand, but bear with me. I will do a quick pass through this code, and then I can explain you in further detail with some numerical examples that makes it much easier to understand that what exactly is going on within the code. So what happens here is we have a bunch of imports, and as you can see, we have block diagonal, causal mask, which is technically, we get the data sliding window attention and causal attention from these xformers package library. So you can have a look at it and see that how these works. So what happens here, we have something called, the first function is something called get cache sizes. And what it does is simply says that, okay, whether I want to, for all the layers, again going back to here, so for all these layers, do I want to have the same sliding window, or I want it to be different? For example, do I want to, let's say for the first layer, do I want it to be, let's say, the window size of 4, and maybe the last layer would be just 2. So what happens would be simply something like this, just only these 2. And it is very common as we go higher up in the layers, we change the sliding window. For example, the first one could be 4. It is usually like a list. It is 4, then it can be 2, again 2, and then, for example, something like 1 or something like that. So all it says here is, okay, number of layers and how I want them to be. Is it a list, repeat this pattern across all the layers, or no, it's just, it's different for each of the layers. This is exactly what happens in this function. But cache input metadata, so this is very important for the next step, which is called cache view, and cache view itself will be directly used in the main code. We will see it in a minute. So this cache input metadata is very important. What it says, it gives a bunch of metadata information about the position of the each token, whether they should be masked or not, whether they should be attended or not. Whether it's pre-filled. Pre-filled means technically, is it the first round that we need to just pre-fill every position or not. So yeah, the positions are, as you can see, a global absolute token indices for rope. To cache mask, it's just it's a list of booleans, true, false, which allows us to know that, okay, this token needs to be masked or not. That's how it works. Cached elements, we have the number of elements per sequence retained in cache. We will see all these in detail in the numerical example. Bear with me. This is, as I said, this is just a simple fast forward through the code. Prefill, mask, and sequences, and the sequences is just how many sequences do I have. So the way that it works is, we don't just give one sequence to the whole system. So it could imagine that your system, I don't know, your Mistral, at the same time, imagine it's a kind of chat system, and at the same time you have 3 conversations. So it is 3 sequences. So you should handle all those 3. So that's why we have sequences, list of sequence length in a batch. So we have something called interval list. So what it does is, just imagine we have 2 tensors. So one of them is A, B, C, whatever that it is, X, the second one is X, Y, and so on and so forth. What interval does is just put them next to each other. So A and X, B and Y, C and whatever, Z, so on and so forth. Why is this part is useful? It's useful because, again, imagine that we have several conversations. In those conversations, now imagine we have the incoming tokens. Those incoming tokens should be appended in the right order to the existing sequences. That's why we need interleaving the existing tokens, or let's say cache, to the new generated tokens that comes in. For example, you can see this as 3 conversation, and when I say 3 conversation, it can be 3 prompts, and these could be 3 inputs that user just started to send. So we need to give the right question or query to the right prompt, append it to the right prompt. This is why we need interleave list. On rotate, again, If you remember, this is technically what that onRotate means. When we get to the 4th position and when we have the next one, so the order is problematic here. So because it is 1, 2, 3, 4 and then 5. But as you can see, we appended to the very oldest position. So we need to unrotate it. So what this unrotate does is just simply puts the right order into this list and makes it 1, 2, 3, 4 and 5. So as you can see, if the sequence list is less than the cache, just return it. If the position is 0, again return the cache. If not, just put it into the right order, which is just this simple concatenation, which is technically putting this into the right order, which we need to repeat it each time that we append a new token, for example. But the main part and the main class, which is cache view, so what it does is simply gives a view into a particular layers, key and value cache tensors, and it just handles the whole returning the correctly interleaved keys and values. Again, I'm gonna do a quick pause here and then we're gonna get into much more detailed example, numerical example, which you can easily understand that what's exactly going on in this cache view class. So imagine we have the cache key and value and metadata. Metadata is very important. Again, don't forget what was the metadata and what we had in metadata. And KV sequences. It's just the sequence of the whatever we had in the cache. So update, how update works and what it does. As you can see here in the stock string, it writes the new key and value tensors into the cache using the cache positions from that metadata. What it does, it just simply flattens the cache and values. We keep the number of heads and head dimensions, and other than that, we flatten the KV, and we try to just add the new tokens, let's say, into the into the right positions. And then what we do, because we have the new tokens, we interleave them. And again, do not forget what interleaved means. We need to put and append the right tokens, the tokens into the right sequences. Again, we will see them in a minute, what it means. And after doing the interleave, we need to unrotate them, because again, this logical sequence of the new tokens when they join into the buffer, it's a bit problematic. We need to do that on rotation, and once we did on rotation, we can just send it back to the rest of the calculation. So I know it's a little bit hard, and I'm not sure if I explained it in the best way possible, but hopefully with this example you can understand it much better. So what I do, we have technically 3 passes here, but I'm not gonna do the first one. The first one is more high level and high overview, which you can go and have a look at it. I do the second one, which I would say it's more, I can say, compact, but also informative. So let's go to this part, comprehensive real world example for, let's say, chatbots, and hopefully if this works. I never tried it. Okay, yeah, cool. Okay, now imagine what we have. Imagine we have 3 conversations. These 3 conversations, we give them all into the system. And imagine the first conversation is just a technical report, the second conversation is product inquiry, or and the third one is just billing question. The initialization could be something like the prompt, or imagine we are in the middle of a conversation, for example. So whatever that it is, the first conversation is 50 tokens processed by now. The second one is 8 tokens, and the third one is 22 tokens. So as you can see, and it is clear, the batch size is 3. The maximum sequence length is 128. So each of these conversations could not be more than 128 size in the sequence. So we have 3 sequences. Each sequence is max 128 length. Number of KB heads, let's say it's 4, and the head dimension is 32. And let's say the new token per step is 1, which is just for simplicity. It's not necessarily like that. So the initial step. So right now in the code, if I want to say, we are technically in the cache view, we are right here. We get the tokens and the cache values, and we have the new values, and we want to flatten them and then update them and then interview and unrotate them. But right now we are in this part. So what happens? We have cache, k and value, and the sequence length is, again, do not forget that it was 15, 8 and 22. So technically the cache tensor would look like 3 sequences, each with a max sequence length of 128, head dim of 4, each head contains 32 dimension, and the same for the cache. And again, about the 3 positions, we have, for the first conversation, we have 15 up until 127, for the second 8 to the rest of the sentence, and for the third conversation we have 22 up until the 127. Now imagine that we have a new user message. So the first one, which was, what was that? It was technical support, product inquiry, and billing question. And now imagine the next token for the first one is what, for the second one is how, and then when. So how they look like technically, because we have a batch of 3, so they look 3 by 4 by 32. Hopefully that makes sense why it is like that. To cache max, if you remember, so right here in the metadata we had something called to cache mask and cache elements and cache positions. Remember them? To cache mask allows us to say that, okay, whether I want to cache it or I want to mask it and just kind of don't look at it. So when we say true, we will attend them and we will look at them and we will bring them in our calculation. And the cache positions, it is 15, 8, and 22. And it is clear why, because these are the next 3 positions. So the first one here was 15 tokens, so that would be from 0 to 14, from 0 to 7, from 0 to 21. So the next positions when the next new token comes would be 15, 8, and 22. And the sequence length again is 1, 1, 1, because there's only one token which comes. But that's not necessarily true for real systems. It could be much more. For example, it could be 3, 10, 12, whatever. Just imagine when you write something to a chatbot, it could have different lengths. This is that part. And now what we need to do is we need to extract the dimension and flatten them. If you remember again, right here we had the flattening part, which I need to have just the heads and head dimension and then flatten the rest. So head dimension, flatten the rest. And the reason why we do that, you'll see it in a minute. So okay, now when we flatten those, we know that for the conversation 1, position 15, the flat index of that would be 0 times 128 plus 15, which is 15. But for the second one, that would be 1 times 128 plus 8, which would be 136. So you can technically see it something like this. Previously we had, let's say 3 sequences, which one of them was fill up until 14. One of them was all the way up to 7 technically, and they start from 0. So, and the other one was from 22, because we flattened them. So now we have something like very long tensor, and this is very ugly tensor. This is the first one, second one, and third one. So technically, when we want to append the new tokens, we now see that, okay, that this new token is 15, which is somewhere around here, 160, 136, which would be something roughly here, and 278, which is roughly here. And the reason why we flatten this, I know it might look a little bit silly, but it's just the computation and those tensor product and multiplications, which is more optimized technically. So yeah, so the flat cache K15 would be the new token for the first conversation. The position 136 would be the new token for the second conversation, and in the flat cache, the position 278 would be the new token for the conversation 3, and the same for values. So now what will happen, the KV sequence lengths, they changed. So we have 16, 9, and 23. And now imagine that we calculate the next token from our attention, or whatever that it is. So technically that's the next step. And we make the XK attention and XV attention. So again, because it is one token, it is the same tensor with this length, 3 by 4 by 32. Again, 4 is the head time, and 32 4 is number of heads, and 32 is the head dimension. And again, if you remember right, where was it? I think it was, yeah, right here, when we do the splitting, why we do the splitting and interwheeling, if you remember. So we have these 3 tokens, but we need to split them and make them look like this: 1 by 4 by 32, 1 by 4 by 32, and again 1 by 4 by 32. And now what we need to do, all we need to do, if you remember again from this interleaving part, whatever it was, we need to append them in the right order. That's why we need this function. We split them, we have 3, it is exactly like X, Y, Z, and previously here we have that A, B, C. So we interleave them, and where was it? Yeah, right here. And then we can split the tokens, unrotate them, and then put them back together. So this is technically, and yeah, here, do the concatenation. So this is technically how it looks within a numerical example. And if you want even a further detailed example, you can go to the next round, which is ultra detailed example, and it literally gives you even the numbers, that how they look like and at each position. And when we do the appending, or I don't know, rotating, so on and so forth, how it looks and how it happens. So this is very detailed. I spent a lot of time to make this. So yeah, I will put it in my GitHub repo and go there and have a look at it. And yeah, technically that's how it works. And this was for this section, which was the sliding window attention, the cache, everything about caching, KV cache, and rolling buffer. And just a quick one, and the last thing, that where that cache and will be used technically, as you can see in the transformers layers, again in Mistral code, we have this cache view right here, and where we use it is technically right down here in the forward pass, and we will give it to the forward pass of the attention. And yes, so technically I would like to add something else to this video, which is grouped query attention, which I can quickly explain. I think that would worth mentioning. So about the just imagine when we have the query and values. So for each query, what we can do in a simple attention, for each query we have one key. So this is the simple format, but what we can do in order to make it even more optimized, for each two query we can have one value, which, so technically they share the value, key or value, and this is called group query query attention, which makes it much more optimized. Or we can even have, I don't know, for every tree we can have one key or value, or even furthermore, if we have one key or value for each query, that's the simple one. If we have something like this, let's say if we have, for example, for each 4 we have one key or value, this is what's called group query attention. But if we have only one, this is, I think, called multiple query attention. And this is just kind of repetition within the keys and values. And on the code where you can see it, again in the transforms layers, if I can quickly find it, so it should be, yeah, right down here in the code. Again, in the next section, when I'm writing the whole code, you can see in more detail that how it looks. I just wanted to give a full quick explanation of how it looks, because it's very simple. It's just repeating the keys and values. There's a function called repeat kv, and what it does simply is just if I can find it right here, it uses a torch function, which is repeat interleave, and it repeats the tensor cells in a given dimension. So how it looks in code in a numerical example. So here, as you can see, imagine that I have a tensor of 1, 2, 3 right here. If I want to interleave it 3 times in the dimension, I think that would be 0. That would be 1, 1, 1, 2, 2, 2, and 3, 3, 3. I just repeated. So it's exactly the same as, again, this visualization. What I do is just I have the tensor, and I just need multiply it. Just use the same thing, so it avoids furthermore computation. So for example, again, I have 1, 2, 3, and I want to let's go for this third example along a specific dimension. Imagine that I have 1, 2, 3, 4, and I want to do the repetition in dimension 0 2 times. So that would be 1, 1, in dimension 0, that would be 1, 2. Then I will repeat it again because it's dimension 2, 3, 4. I repeat it again, 3, 4. But if I do it in the dimension 1, that would be 1, 1, 2, 2, 3, 3, 4, 4. So hopefully you have a better understanding of how this repeat KV works down here. So yeah, this was the code and explanation for the sliding window attention, rolling buffer, group query attention, and what was the other one? KV cache. And hopefully it was informative for you. And again, I will put all this material, PDFs and visualizations in my GitHub. Feel free to have a look at it, and don't forget to like and subscribe to the video. And yeah,